Okay, so tonight we have first um, Tom Wannamaker, and he was a submariner for 6 years, and then he got his bachelor and his master's in mathematics, and he taught 2 years, studied 2 years towards his PhD. He taught at his alma mater, University of Houston. He was an adjunct instructor at the downtown college and at UCCS. And he is married to the beautiful Tommy, and they will be celebrating their anniversary 50th in December. So, Tom, come up and take it away. Oh, encourage him. Yeah, definitely.
All right. A friend of mine called me yesterday and said, let's go to lunch. And I said, no, I got to work on my slides. What are you doing? He said, Maxwell's equations. Oh, I didn't know you were teaching again. And I said, well, I'm not. I'm giving a presentation at church. And he goes, what? So this is about my passion. And my passion is mathematics and the history of math and science. And so I didn't start out that way. I mean, I was just a kid. I wasn't a math whiz or anything like that. But I went to high school in a Catholic seminary. And we got 4 years of science, 5 years of math, and 6 years of languages. And so that was a pretty classical education there. And that's where I got hooked. It was just, oops. That's what's impressed me all these years, is the architecture of the universe, the symmetry of mathematics, the construction of it, the elegance, the simplicity of it. That's what keeps me going. So one of the big things that has happened, not in our lifetime, but recently, was Maxwell's equations. And so that the physicist Richard Feynman, the famous 20th century physicist, he said that Maxwell didn't just change the world, and that, by the way, that's the latest biography of James Clerk Maxwell, is the man who changed the world. Feynman said he didn't change the world, he just opened up an entirely different world. And so everything you see now in terms of radio, television, wireless communications, everything owes its existence to Maxwell's equations. So let's go ahead and get started here. So this is a little bit, I thought it was going to be a little bit larger, so I'll just read it real quick. Maxwell's equations are a set of 4 equations that together form a complete description of the production and interaction of electric and magnetic fields. These equations are named for James Clerk Maxwell, the Scottish physicist, whose pioneering work during the second half of the 19th century unified the theories of electricity and magnetism and light. At the beginning of the 19th century, electricity and magnetism were lab curiosities. And things like, flying kites with a key on it just so you could, make something happen. And there was no connection observed between electricity and magnetism. And quite frankly, most of the scientists didn't believe it. You know, if you asked their opinion, they would say, no, don't see the connection there. Alessandro Volta was an Italian scientist who built the first battery. Back then, they weren't called batteries, they were called voltaic piles. It's like copper and zinc. Discs interspersed with cloth soaked in salt water. But what happened was he would make those. For any scientist who asked for them, he would make one and send it to them. And that allowed scientists to begin to experiment in the lab with a continuous source of electricity. So that's kind of got the ball rolling. So I'm getting a little bit ahead of myself right now. The unification that Maxwell did, the unifying the theories of electricity and magnetism and light, that's called the second great unification. The first great unification was Newton unifying physics and astronomy. And the second great unification is electricity and magnetism and light being shown as fundamental features of the same underlying concept. And we're in the middle of the third great unification, which is trying to figure out how to make electromagnetism work with the strong and weak nuclear forces and gravity, you know, to unify all that. And it's a long haul. It's not going to happen anytime soon. All right, so Maxwell's equations, those four right here, okay? I'm not going to make you recite them. I thought what I would do is just simply go through the four of them. The first one is Gauss's law of static electric fields. What it says is that it defines the relationship between positive and negative charges. Things move, things diverge, remember that word diverge, from positive charges to negative charges. And then the electric field depends on the charge distribution. And if you look at the next page right there, you can see on the right-hand side the different field distributions. Depends on whether you got two negatives close together, they repel. A positive and negative, they attract. But you're always moving from positive to negative. If you have unequal charges, then you get those kind of interesting field patterns. For magnetic fields, it's simple. All magnetic lines are closed loops. And they go from North Pole to South Pole, and that's it. So when you get back here, that's the second law, which is the Gauss law of static magnetic fields. That defines the relationship between magnetic poles and the magnetic field lines. They're always closed loop. Very simple. Then the third law is Faraday's law of electromagnetic induction, and that says that a changing magnetic field produces a circulating electric field. And then the last one, the Ampere's law, it's actually the Ampere-Maxwell law. An electric current produces a circulating magnetic field, Also, a changing electric field also produces a circulating magnetic field. So let me look at the pictures again. Okay, that's a picture of Ampere's law. And what happens is you have a current going through a wire. It creates a circulating magnetic field. And the reason why they found that out is by accident. Yeah, Hans Christian Ørsted in 1820, he was working on the conductivity of different materials conducting electricity. And so he was getting prepared for an experiment, and he turned on his electric circuit, and there was a compass nearby, and the compass jumped. And that was shocking to him. He didn't understand that. So he went and demonstrated that several times. And André Ampère, when he came to the French Academy of Sciences and showed this, Ampère said, yeah, I bet you I know why that is. And so Ampere's law said that if you have electricity running through a wire, it will create a circulating magnetic field. And if the current's going the other way, it'll curl the opposite way. So let me try this. Save the best for last. That's Faraday's experiment. Faraday was really the first one who used the word electromagnetic. They saw the connection, and what he did was if you close the switch there and run the battery, and you run electricity through that current, that creates the magnetic field, which changes and induces a current on the right-hand side, completely unconnected circuit. Faraday he used the word electromagnetic. He used the terms field and lines of force, and he was the first one to do it. And actually, when you think about it, we could have been talking about Faraday's laws in Faraday's equations instead of Maxwell equations. But Faraday didn't have any mathematical background. He could just talk about these things, and everybody says, well, if you don't have the equations, then sorry.
You got 8 minutes.
Got 8 minutes? Okay, got to go fast. All right, so the other side, you'll see in those equations, there's that kind of upside down triangle. That's the del operator. It's a differential operator. This is the mathematics. This is the math lesson. That's an operator on a vector field. On a vector field, everything has magnitude, distance from the origin, and a direction. Kind of, if you look at the weather maps, and you'll see things moving around like wind or temperature. It's the same thing. Every position in the field has a magnitude and a direction. And so the two operators, del dot and del cross, those are like derivatives in calculus. If anybody who's had calculus, in calculus you're always concerned about distance, velocity, rate of change of distance, acceleration, rate of change of velocity. You're concerned about rates of change with respect to time. So what the two operators do, the two operators, that del dot operator measures the instantaneous rate of change in the strength of the vector field. Remember, it's at a maximum when you're near a positive charge, and when you go away from it, then it's going to weaken, and then as you head toward a sink, a negative charge, then it's going to increase in strength in the opposite direction. And then the other one, the del cross, that's the cross product. And what that does is it tells you the degree of local spinning. This is the rotating magnetic field. They used to call it vorticity, but that's, too long a word. The name of that operator is curl, because the magnetic field curls around an electricity running through a wire. So, I'm not going to walk you through that math there. So the big question is, if it's two of Gauss's laws and Faraday's law and Ampere's law, then why do they call it Maxwell's equations? Okay? So we go through a little bit of history here. Math lesson's over with. We're just talking about history now. So in 1785, Charles Coulomb was experimenting with measuring electric force between charged vehicles, or charged objects. And in 1813, Carl Friedrich Gauss was a mathematician who was looking at the physics of it. How do you calculate the force of attraction or force of repulsion between these charged objects? Excuse me. And he pretty much nailed it down, and then published his findings in 1835. He wrote it in his private papers. He didn't publish it. So it didn't get published until 1867, when they were going through his collected works, and they found out all kinds of things that he had studied and proved and demonstrated, and it never saw the light of day. So that particular part of it, Gauss's laws, didn't come out until 1867, which was 2 years after Maxwell published all of his work. So because it traces back to his original work, then he gets the credit for it. So now Ampere published his circuit law, that the rotating field. He published that in 1826. And when Maxwell put his work together, put the entire theory together, Ampere's work was incomplete. That Ampere talked about the field rotating around electricity conducting up a wire, but what Maxwell demonstrated was you can also do that by a changing magnetic field. So he added that. Okay. And then Faraday was talking about fields and lines of force and all that good stuff, but he didn't have the mathematics. And so what Maxwell did was he decided he was going to write the field equations for Faraday. And in fact, he and Faraday, even though there was 35, 40 years difference in their ages, they were able to communicate. And so he built his original first paper in 1856 on Faraday's lines of force. Then he further expanded it. He threw in the addition to Ampere's law, and then he rewrote all of his work, 1861 through 62, to put the entire theory together, and then published it in 1865, the dynamical theory, where he posited that light is indeed an electromagnetic wave, and that when these things work, it's not the old Newtonian picture of, well, you just wave a magnet in a room and it impacts everything, and it's all instantaneous. I said, no, it's not instantaneous. It's travels at the speed of light, but it does take time to get there. So,
Quickly.
yeah. Yeah, Maxwell's work, in fact, opened it up for Einstein for his relativity. If Maxwell had lived, he might have discovered special relativity on his own. And when Einstein was praised for, the greatest person since Newton, he stood up at the centennial of Maxwell's birth and said, I stand not on Newton's shoulders, but on James Clerk Maxwell.
We do have time for questions.
There you go.
Okay, we're going to hold off on questions. We're going to give you 2 minutes to get this.
All right, 2 minutes.
Not yet. He wants to read his last thing. Go ahead.
Well, I'm going to go back right there. Okay. The physicists up to that time were figuring out mechanical waves and force distributions and all this kind of good stuff. And what Maxwell found out was that this interplay of transverse waves, transverse meaning the electrical field interacts with the magnetic field, and that is how waves are propagated. No medium required. Huh? No. No. At the antenna, you have, you have varying frequencies or varying currents. That's your frequency. But how does it propagate? It's through the transverse electromagnetic and or the electrical wave, the wave through the electric field transverse to the magnetic field. That's how it propagates in free space, in a vacuum. So no medium required, and at that point there was no medium. So now we skip the part where Maxwell had 20 equations and 20 variables. And a guy named Oliver Heaviside invented the vector calculus and those differential operators and reduced it to 4 equations in the unknowns being the electric field and the magnetic field. And within 4 or 5 years, that was the universal adoption.
Okay.
And now you can get it on a coffee cup.
All right. Good. All right. Does anybody have any questions for Tom? We're going to take 3 minutes for that, and then we'll have our Becky come up.
So when light goes through water, does it get wet?
No.
No, doesn't get wet. Anybody else? Oh,
Yeah.
Okay, here comes Tim and then Holly. Okay.
Did these guys set it all up for Edison? I mean, did he take a lot of what they already put together to?
No, that whole piece of history has to do with sources of electricity and transmission of electricity and distribution, for power and things like that.
Right.
Edison was barking up the wrong tree because he thought direct current was the right way to go, and it was not the right way to go.
Yeah. Okay. I just thought they might have set up a bunch of the groundwork for him, but not connected.
No, in fact, the guy Heaviside who rewrote Maxwell's equations, he was big on transmission theory. He invented the coax cable, for example.
Yeah.
And he also invented that little coil that goes into the handset in order to reduce the chatter and the buzz.
Yeah. Yeah.
That was Heaviside.
Okay. Yeah. Thanks, Tom.
I have a question, Tom. As far as like your passion for this, what makes this so beautiful? Like, what is it about this that really sparks you and makes you say these laws, this set of things, are what sparks a passion?
Well, that's it right there. When you start at the beginning of the 19th century and electricity and magnetism are just, lab oddities, and then there's this accidental discovery and this accidental discovery, and something else happens and somebody else grabs this and says, well, it wasn't quite right, so we'll just tweak it a little bit. And then it grows and grows and grows, and then all of a sudden, wham, somebody builds the tools to kind of catch up with all the work that's been done, and then it winds up being described elegantly in, those are simple lines, but there's a lot going on there.
You said he had proven, Merrick was his name? Merrick, right? The Scottish gentleman.
James Clerk Maxwell?
Maxwell,
Yeah.
excuse me, Maxwell. You said he had proven that light was a wave?
No, he posited that it was a wave.
Okay, he did not prove it, okay.
No, he didn't. He published all of his stuff in the 1860s and then wrote a 2-volume summary of his collected works in 1873, and then he died at the age of 48 in 1879.
But he was convinced it was a wave.
He was convinced it was a wave. He said it works out. We have calculated the speed, and he says the speed matches the known measurement of the speed of light. He said that cannot be a coincidence.
How does that relate to the ongoing debate of the duality of light, that it's a particle versus it's a wave?
Light has both wave-like and particle-like properties. That's it. Young's experiment showed that it's a wave back in the early 1812 or something like that, where they two independent light sources through slits, and the interference pattern says, geez, it's a wave. And then the experiments, the photon experiments that Michelson and Morley did later on said it's particles. So.
Did you have a question?
I just have one thing I want to say. I think I get your passion for this. The principle that seems to come out of here for me is that we have a tendency to think that knowledge brings meaning, but really knowledge comes out of meaning. Meaning was established right there. And in all these guys' minds and the stirrings of their heart and the work of the Spirit, they created knowledge out of meaning that matched. Because before, what people thought was knowledge didn't match. Mm-hmm. Yeah.
Well, there was an awful lot of facts laying all over the place, and out of that comes the truth. And this is a quote from James Clerk Maxwell. He said, "Truth is more than just about the facts."
Yeah.
Great. Thank you, Tom.
All right.
Great.
Appreciate it. Love stuff like that. All I could think of while he was talking was because math was not my big skill, I actually got a C by bribing my teacher. But it made me think about the mysteries that are all around us that come to light, and that's pretty cool.